Welcome back to Basic Electronics. We have looked at the flash ADC in the last class. We will now look at some other commonly used ADC types, namely successive approximation ADC, counting and tracking ADCs, and dual slope ADC. Okay, let us start. Let us now discuss a very important issue which is very closely related to analog to digital conversion, and that is sampling of an analog signal. In many applications, when we convert an analog signal into a digital signal, we want to use digital signal processing on this digital output, and in these cases sampling is absolutely essential. So let us first see what sampling means, and then we will see how to achieve it. Here is our analog signal, the one that is varying continuously, VA, and we have a clock, and the clock has very narrow pulses, ideally with 0 width. Now what we want to do is, when the clock is high, we want to sample this analog signal, and when the clock becomes low, we want to hold that sampled value constant, like that. When the next clock pulse comes along, we want to now sample the analog voltage again and then hold that value constant, and so on. So this process is called sample and hold. And these are the samples which are used for digital signal processing. Now, digital signal processing also requires digital data, and therefore these samples need to be converted to a digital output, and that we do using an ADC, which is not shown in this figure. Alright, here is a schematic representation of a circuit which can be used to perform the sample and hold operation. This is the input analog voltage, and that is the sampled analog voltage, which will be sent to an ADC for conversion to a digital number. Now this part is not shown in this figure. Here is a switch which is controlled by this clock here. When the clock is high in a short interval here, the switch closes and the capacitor gets charged to VA. Now this charging process is very fast because the switch has a very small resistance, ideally 0, and therefore the capacitor voltage, which is our sampled voltage, simply follows VA of t, and that is what we show over here. During this interval, when the clock is low, the switch is off, and now the capacitor voltage cannot change anymore because there is no path for the capacitor to charge or discharge, and that corresponds to this hold operation here. So that is how this circuit performs the sample and hold operation. Here is a summary of the points that we just made. In addition, notice that the switch S is typically a field effect transistor or a CMOS pass gate, this switch here. And in addition to this basic circuit, we may need op-amp buffers both on the input side and also on the output side to minimize loading effects. So this in a way is a more complete circuit. Another commonly used ADC is the successive approximation ADC. Here is the block diagram for a 4-bit ADC. This register holds a binary number D3, D2, D1, D0. There is a 4-bit DAC here which converts this binary number to an analog value, which we have called VO DAC, output voltage of the DAC. That gets compared with VA, which is the input analog voltage, which we want to convert to the digital format. So these are the operations involved, and now let us see how this ADC works. So here is the algorithm. We start with D3, D2, D1, D0 equal to 0, 0, 0, 0. That means all these bits are set to 0. And we define one integer I. We set that to 3. Set t of I equal to 1. Keep other bits unchanged. That means since I is 3, we're going to set D3 equal to 1, this bit here, and keep the other bits D2, D1, D0 unchanged. That is, they will stay at 0, 0, 0 in the first iteration. Okay. Now if VO DAC is greater than VA, that is if C is equal to 0, this variable here, then set D of I equal to 0, else keep D of I equal to 1. And then follow this process by replacing I with I minus 1. So that is the algorithm, and it will become more clear when we look at an example in the next slide. At the end of 4 steps, the digital output is given by D3, D2, D1, D0. So at the end of 4 steps, the contents of this register will be the digital output that we are looking for. Let us now consider this example. It's a 5-bit ADC which uses a 5-bit DAC, and the output of the DAC, which is VO DAC, is plotted over here. And if this number is 0, 0, 0, 0, 0, then the output of the DAC is 0 volts here. If this number is 1, 1, 1, 1, 1, that is decimal 31, then the output of the DAC is 31 times K, that one, where K is proportional to the reference voltage applied to the DAC. Okay, our input analog voltage is shown by this line here. We will call that VA. Now the algorithm begins like this. In the first step, we set this MSB equal to 1 and all other bits equal to 0. And what is the DAC output then? This number is decimal 16, so 16K is the DAC output as shown over here. Now we compare this voltage with the input analog voltage using this comparator, and we find that VA is higher. So the comparator output C is 1, and therefore we keep this D4 as 1 and then go to the next iteration. In the next iteration, we set the next bit, that is D3, equal to 1, and once again compare VO DAC and VA. What is VO DAC in this case? It is 1 times 2 raised to 4 plus 1 times 2 raised to 3, that is 16 plus 8, or 24K. And now we find that this VO DAC is higher than VA, and that gives us C equal to 0. And since C is 0, what we do is reset the current bit, that is D3. That means make D3 equal to 0 and then go to the next iteration. So in the next iteration, we have D3 equal to 0 here. And we continue like this. In the next step, we make D2 equal to 1 and we find our VO DAC is now 20K. VA is higher than VO DAC. C is 1, and therefore we retain D2 equal to 1 in the next step. Now we set D1 equal to 1 and find that VA is higher than VO DAC. So therefore we retain D1 equal to 1. And finally, we make D0 equal to 1. We find that our VA is now lower than VO DAC, and therefore we reset D0. So at the end of the 5th step, we know that the input voltage corresponds to 10110, that is 10110, because D0 has been reset. one small correction is required. For the digital representation to be accurate up to plus minus half LSB, delta V corresponding to half LSB is added to VA. And you can read more about this in this reference. Let us now look at how a successive approximation ADC can be implemented. This is the example that we considered in the last slide, and this is how it can be implemented. We have an input voltage VA prime of t, a time varying analog voltage, and this voltage is fed to a sample and hold circuit to produce this V sub A, the same as this VA shown here. Now this VA is expected to be held constant throughout the conversion process, and therefore we must adjust the frequency for this sample and hold circuit, the clock frequency, so that VA remains constant throughout the conversion process. Alright, so that VA is one input of the comparator. The other input, this one, comes from the DAC, and that we have called as VO DAC over there. The output of the comparator goes to this control logic, which figures out which binary number should be loaded into the n-bit successive approximation register in the next clock cycle. This control logic gets this clock signal, and that should not be confused with the clock signal for the sample and hold circuit. This clock signal essentially controls the speed of this conversion process. As an example, let us say that this clock has a frequency of 1 megahertz. That means the clock period is 1 microseconds. And let us say that it takes 20 cycles, 20 clock cycles to complete the conversion process. That means this entire conversion from analog to digital is going to take 20 microseconds. And therefore we must make sure that this VA is held constant for at least 20 microseconds. The output of the n-bit successive approximation register, or SAR in short, is sent to the DAC, and it also serves as our final digital output when the conversion process is completed. So that is the overall block diagram of the implementation of the successive approximation ADC. Let us make a few remarks. Each step, that is setting of the SAR bits, these bits for example, and comparison of VA and VO DAC, this comparison, is performed in one clock cycle, and now we are referring to this clock signal here, and therefore the conversion time is n cycles. So if this clock has a period of t, then the total conversion time is n times t, where n is the number of bits, and that is irrespective of the input voltage value VA. Now this time, the conversion time, is definitely larger than that required for a flash ADC, but as we will see, it is better than some other ADC types. Commercially, successive approximation ADCs with built-in or external sample and hold are available for 8 to 16 bit resolution, and the conversion times are typically a few microseconds to tens of microseconds. So these are considered medium speed ADCs, and they are useful for applications such as speech transmission with PCM, for example. PCM is pulse code modulation. Let us now discuss the counting ADC, or also called the digital ramp ADC. Here is the block diagram. It has an n-bit counter with a reset input and a clock input. The output of the counter, all these bits, is given to an n-bit DAC, which converts it to an analog value which is called VO DAC over here, the output of the DAC. This is our input analog voltage that goes through a sample and hold circuit, and that is applied to the plus input of this comparator. The minus input is VO DAC. The output of the comparator, C, is ANDed with the clock signal, and that serves as the clock for the counter. So that is the block diagram, and now let us see how the ADC functions. Alright, the start conversion signal, this pulse here, clears the counter. That means all these bits are reset to 0. Counting begins, and VO DAC increases with each clock cycle, the output of the DAC here. And that VO DAC looks like this because the count is increasing with every clock cycle. When VO DAC exceeds VA, C becomes 0 and counting stops. Let us look at this point. This is our input analog voltage after sample and hold, and at this point our VO DAC exceeds VA. When that happens, C becomes 0 and the output of this AND gate therefore becomes 0, and the counter does not receive the clock, so counting stops. Now at this point, the binary number that we have here in the counter is the digital output that we are looking for. If VA was larger, for example somewhere here, then this counter would count for some more time and then stop. So that is how this counting ADC works. Alright, so this is a very simple and therefore attractive scheme, but the conversion time depends on VA, as is obvious. If VA is here, then we need that many clock cycles. If VA is here, then we need a larger number of clock cycles. B, it is a slow process, and in the worst case it takes 2 raised to n minus 1 clock cycles. So if n is 10, for example 10 bit ADC, then this number is 1024 minus 1. That's a large number of clock cycles. And to improve upon the speed, we have this ADC called the tracking ADC, and that is what we will see now in the next slide. Here is the block diagram of a tracking ADC, and it is quite similar to the counting ADC which we saw in the last slide. The only difference is that here we have an up-down counter, and if you recall, in the counting ADC the counter always started from all bits equal to 0, that is decimal 0. Here that is not the case. So let us see how this works. In this case, the clock is always provided, and whether the counter counts up or down is decided by this output C of the comparator. Now for the comparator, V plus is the input analog voltage VA after sample and hold, and V minus is the same as VO DAC, the output of the n bit DAC. Alright, let us take an example. Say VA is larger than VO DAC, then C would be 1, and that signals the counter to count up. Then the count increases and VO DAC increases. So in this manner, VO DAC tries to catch up with the input analog voltage. In the other case, when VA is less than VO DAC, the comparator output is 0, and that makes the counter count down. That means the count decreases with time, and therefore the output of the DAC, VO DAC, will also decrease with time. So once again we see that VO DAC is trying to catch up with VA. In the steady state, VO DAC oscillates around VA as shown over here. This is our VA and that is our VO DAC. Now in this clock period, for example, VO DAC is higher than VA, so the counter will be asked to count down, So the count has gone down, so VO DAC has decreased by 1, and now we find that VO DAC is less than VA. So the counter will be asked to count up, and so on. So that gives rise to these oscillations around VA. These oscillations may seem like a problem, but notice that the oscillations are only in the LSB, this least significant bit of the counter, and therefore if we have a large enough number of bits where all these other bits remain constant, then this change in the LSB may not really matter in a real application. Okay, here is an example of what happens if VA changes from one level to another. In this case, VA has increased, so the counter then starts counting up like that, and finally when the counter catches up with VA, that is VO DAC catches up with VA, then the steady state is reached once again. Alright, in summary, the counter counts up if VO DAC is less than VA, else it counts down. If VA changes, the counter does not need to start from all zeros, so the conversion time is less than that required by a counting ADC, which we saw in the last slide. And this kind of ADC, the tracking ADC, is used in low cost, low speed applications. For example, measuring output from a temperature sensor or a strain gauge, where quantities don't vary very fast. The time scale may be in the milliseconds range. There is another useful ADC type, that is the dual slope ADC, and it is often used in handheld multimeters, for example. The basic principle of a dual slope ADC can be illustrated with this circuit, which is an integrator with VO equal to minus 1 over RC integral VI dt, as we have seen earlier. A switch is provided in parallel with the capacitor. When the switch is closed, VO is the same as V minus, which is the same as V plus, that is 0 volts. So when the switch is closed, VO is forced to become 0. The input voltage for the integrator, that is VI, is either VA, the input analog voltage, or it is a reference voltage VR. And there is a switch which connects these two nodes or these two nodes. Alright, let us now see how this ADC works. Let us say that at t equal to 0, we reset the integrator output to 0 volts by closing S momentarily. So we close this and open it very quickly. So that makes the output voltage equal to 0. So that is our starting point. We should remark here that this switch is not a mechanical switch. It is an electronic switch, for example a transistor, and it is operated using some control logic which is inside the ADC chip, and it needs to close only long enough so that the capacitor gets discharged. So at t equal to 0, the switch has been closed and opened, and now the integrator can start integrating. So in the first phase, we put this switch in this position. So our VI is equal to VA, that is the input analog voltage which we want to convert to the digital format. So the integrator starts integrating VA, and that happens for a fixed interval t1. Now let us assume that VA is positive and see what happens. This is t1, and since VA is positive and constant, the output voltage is a straight line with time with a negative slope. That slope is minus VA by RC, that comes from this equation. Alright, so what is the value of VO at t equal to t1? That is simply minus VA times t1 by RC. and at this time, that is t equal to t1, we change the position of this switch from VA to VR. So VI is now equal to VR. And if VA is positive, then we choose a VR which is negative and also larger than VA in magnitude. So then what happens is VO starts increasing now because VR is negative, and this slope in magnitude is larger than this slope because our VR is larger in magnitude than VA. And this goes on until we reach 0. And let us say that we have some means of measuring this time interval t2. Alright. Now from this figure we can conclude that VA times T1 by RC is the same as mod VR times T2 by RC. We have mod VR here because VR is a negative voltage. And from this equation we can say that T2 is T1 times VA by mod VR. Now T1 and mod VR are constants. Therefore T2 is directly proportional to VA. In other words, T2 gives a measure of the input analog voltage VA, and that we convert into a digital format. So in the dual slope ADC, a counter output which is proportional to T2 provides the desired digital output, and we will see how that is done. Here is the actual implementation of a dual slope ADC. This part we have seen earlier, that is the integrator. The output of the integrator VO is the same as V minus for this comparator. Its V plus is 0, and the comparator output is ANDed with this clock signal, and the output of the AND gate serves as the clock for this n-bit counter. This counter is an up counter, binary up counter, and let's say it has 4 bits. To illustrate what happens, it starts off at 0000, then 0001, etc., and the final maximum count is 1111, and after that it goes back to 0000, but then it indicates that there is an overflow, and that signal is used to change the position of this SPDT, the single pole double throw switch, from A to B. Alright, so let us go through the operation of the dual slope ADC now. We start with the counter with all bits equal to 0, decimal 0, and with the SPDT in position A. That means our VI for the integrator is equal to VA. So the counter starts counting and the integrator starts integrating. VO starts going down like that. The counter counts up to 2 raised to n, at which point the overflow flag becomes 1. That is this point here. And at this point the SPDT switches to position B, and that control of course comes from this overflow flag. So after this we have VI equal to VR. Alright, now let us figure out what T1 should be. We know that there are 2 raised to n clock cycles in this interval, and therefore if Tc is the clock period, T1 is 2 raised to n times Tc. Okay, after this point the counter starts counting again from all bits equal to 0. The output of the integrator starts rising because our VR has the opposite sign. So VR is negative in this case, and when this VO crosses 0, what happens is the comparator output becomes 0, and we have 0 over here as the clock. So this clock signal does not reach the counter and the counter stops counting. And the count that the counter holds at this time is exactly the digital output that we are looking for. So as we have seen in the last slide, this T2 is proportional to the input analog voltage VA, and this counter simply converts that T2 into the digital format. So that is how this dual slope ADC works. It should be clear that the dual slope ADC is a slow ADC. Its conversion time is T1 plus T2, and in the worst case T2 can be nearly equal to T1. So that gives a total conversion time of 2 times T1, or 2 raised to n plus 1 times Tc, where Tc is the clock period. Having said that, let us also mention that the dual slope ADC has a major advantage in terms of noise immunity. Let us try to understand what that is. The analog voltage which we are trying to convert to the digital format is expected to be constant throughout the conversion process. However, there is some noise riding on it, and the noise can be both positive and negative. When we integrate VA, what happens to the noise? Because it is both positive and negative, its integral is approximately 0 or a very small value, and therefore it does not reflect in the digital output. And that is a big advantage of the dual slope ADC, and that is why it is popular in applications such as handheld multimeters. To summarize, we have seen the successive approximation ADC, counting and tracking ADCs, and dual slope ADC. We have also commented on their advantages and limitations. That brings us to the end of this course, but we have only scratched the surface so far. It is important to remember that electronics is 10% theory and 90% practice. When we actually want to build a product, we need to know several practical matters, such as which op-amp meets the performance criteria, how to pick a diode or a BJT for a given application, how to design a PCB, and so on. Is there an alternative solution which may be better in some way? This course will get you started, but you need to pick up many things on your own to become a practicing electronics engineer. Fortunately, we have an excellent resource, the internet, and there are some excellent books written by people who have worked in the area for a long time and built their own circuits. So you can make use of all of these resources. I wish you all the best in your careers. Goodbye.